Before the seminar starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
The title today is the Algebraic Reasoning Seminar. We had our 10 workshops. This is a seminar. And the difference really is you get time to talk to each other. So what I'd like you to do in your group there are 20 questions in the competency test. I don't want you to feel under pressure to discuss all of them. But you will find that once you start looking at these questions, they're the classic misconceptions that you will have seen in class over and over and over again. So some questions here that you can use in your group to focus your discussions. First one is, you'll be able to predict the error usually in the question, what's the student thinking behind the error? Why did they make that particular mistake? Number two, how is it possible to get the other answers? Because I think one of the strongest features of this test are the incorrect answers. They're tempting wrong answers, if you like. And the third question is the easy one. What are the implications for my teaching? How do we fix these issues? Because some of the questions that you're going to discuss in this test have been mistakes in the Leaving Cert for 30 years. Same algebraic errors shown up for 30 years. So how do we fix these problems? So I'm going to give you maybe 15 minutes to discuss in your groups, and I'll come around and see what you're at soon, okay? Can I get us to come back together as a group, please? And largely what's happened there in your discussions will focus what we're going to do. So I wanted to look at a selection of the questions and just have a general chat around them. Here's the first one. Where do you think the issues were with the first one? Because we took these questions and we gave them to 30 second years in Cavan last September. So what did you think was the most difficult question? Definitely the third one. What's the issue with the third one? They have to, they're going into integers. They're forced into negative integers there to solve it. Here's some students' work. So look at this student first. They're fully right. In particular, focus on that part we were saying could be the tricky bit. So they've put -3 in and -3. A teacher in Athlone said she had a girl do this with the same question. Put these numbers in. So 20 in the first box and -26 in the second box. Clever, isn't it? Yeah. I'll kill that 26 and then it's a really easy sum for me to do. So you know, you could argue that student may be a level above in terms of abstraction to this one here. Maybe there's a remnant still from primary school of the same number must go in the box. You know, when they solve very simple equations at primary. Second student, I think, is a really big example for us because it points something out. Look at the third part again. So this student filled in 20 here and 6 here. What's happening? Okay. Right, so Phil is saying there they're adding the 17 and the 3 to get 20, and it's almost as if this is perceived as an equal sign, isn't it? Would you guess what's going on there? Well, the question said integers, so they had that hint. Yes, the researchers would say, here's the issue. The most used and abused symbol in all of mathematics. The humble equal sign. And you know what? It means something different in primary school at what it does in secondary school. We have a 5-year-old in senior infants and they've met the equal sign for the first time. And the equal sign at primary level generally is, it's the symbol or the signal to do something. You know, get the answer. perform this sum. So for some students it takes them a while to move from the primary notion of it to what we want. I mean, what do we want as the equal sign? That it's balanced, the left hand side is the same as the right hand side, and they reckon that it takes some students quite a while to get to that. Like I had a teacher at one of the seminars say to me, in a resource class with a first year student, that was easy, this was difficult. Because the student's prior experience was the calculation's always on the left and the answer's always on the right, and you know what connects them up? The equal sign that's in the middle. I mean, can you imagine giving this question to a student, okay? 7 plus 2 multiplied by something gives you 31. And they work it out. And then you say to them next, okay, will you try this question for me next? 7 plus 2 multiplied by something, take 9, is equal to 31, take 9. Like their answering there will tell you a lot about how they perceive that equal sign. It's the same question, isn't it? So it's definitely, if you're looking at it in terms of a relational idea, well, both those sides are balanced. But if the student has started from left to right, maybe they still have this notion of the equals as here's what you do, or work out the sum. Have you ever had a student do this type of work as well, like a running equal sign? First years are guilty of it sometimes, working across the page the whole way. Or dropping an equal sign into a question. Like we discussed it there in a few of the groups, the equals will show up because, Phil, you said the student, you know, I have to get an answer. There must be an answer. This type of work, you know, this type of example here. You'll even see it at Leave Insert, calculus, and the left-hand side is all these equal signs running down. But the running equal sign, do you know who's really guilty of this? Well, here she is. Does anybody know who this is? Rachel. Well done, Rachel. It's usually a male who tells me what her name is. Every day in the numbers game on Countdown, you'll see this. So 6 take away 2 is the same as 4 take away 7 is the same as 28. So 6 take 2 is the same as 28. So that's the first idea today. Maybe this equal sign isn't as simple as we all think it is. And just to say to you, I'm going to talk to you a lot about ideas today. As usual, take the ones that you like and leave the rest behind. Okay? Here's an algebraic misconception. It's in pictures though, and I want you to tell me, have you met this in the classroom yourself? So if you do have 3 cows and you add 5 boys to it, when you get them together you get 8 cowboys, isn't it? And that's in the research too, because the likes of question 3 on your competency test, which is just gathering up terms, we had a few students give us 11xy. So students like to compress. One girl told us that 6x minus y couldn't be an answer because it's got 2 parts to it. And in maths there's only one part to your answer, isn't it? And it's at the back of the book. And it's amazing that something as simple as gathering up terms can be such an issue for some of our students. Like Anya, you were saying there you thought it was integers could be part of the problem. With that, the signs and coping with negatives and so on. So, I don't know, maybe we need to think about, particularly in algebra, should we always represent symbolically? You know, if you were to walk into a typical Irish maths lesson on algebra, you probably wouldn't see many pictures on the board. And apparently we've got more visual learners now than ever. So maybe we need to think about some of the time drawing a picture of what's going on. I remember my own maths teacher at school. I was very lucky. I had a Christian brother teach me maths for Leaving Cert. And looking back on it, he was an extraordinary maths teacher. He was obsessed with geometry. And everything was linked to the shape of what you were talking about. So, you know, typically, even with number, what type of numbers are these? Perfect squares. Square numbers, because I can represent them as physically as squares. What about 1, 3, 6, 10? They're triangular numbers. I can represent them as triangular numbers. The likes of 12. Rectangular? Yeah, interestingly, the Greeks used to call those rectangular numbers because whatever pair of factors you pick, the pair of factors, the numbers are different to each other. So if you represent this as 3 by 4, then physically you're talking about a rectangle with those dimensions. And some of the ideas that he taught us in class still stick in my head. Like, take this as an example. The square root of 49. Generally, people are looking for, find a number that when you multiply it by itself, you get 49. But this teacher's take on it was this. There's a square. The area is 49. This question is asking you how long is the side. So visual or geometric. And the answer is straightforward enough. It's 7. What I loved about his teaching as well was he was big into the language of the subject. So I remember him talking about the likes of square root. It's easy to see why square is there, but why is it called a root? Why is it the square root? Well, here's what he told us. It's the root because the square grows out of the side of length 7. So, and I've looked it up since, and apparently that's what the explanation is. So we get to algebra then, and the very first lesson he does with us in algebra, he tells us what our misconception is going to be. That we're going to mix these two up. You're going to mix up x squared and 2x. So he drew them for us. He said, x squared looks like this. It's a square of side x. And 2x, well, x itself generally has this shape. It's a rectangle of side x by 1. And here's what 2x looks like. So does anyone know there what he was really talking about? But which models was he, or classroom resources that some people have in their schools? You seen those before? These algebra tiles? He was talking about algebra tiles. That, this is what x squared looks like. And this is what x looks like. And what's lovely about these is if you reverse them, that's negative x squared, and that's negative x. And then you have these blocks here representing single units, 1 by 1. So what I'm going to try and attempt to do today, as we move through the work, I'm going to try and attempt to layer a geometric aspect to the symbols as we move through it. Okay, because I think that's important, that if some of the students can think about these ideas in terms of pictures, it might help them. Here's what this question looks like visually. So here's your 2x. Here's 3y. So you can see it's a different rectangle for y. Then you have 4x. And anybody suggest a way that I could subtract 2y? So what could I do? So I've done the geometry of the first 3 parts. How could I take away 2y? Take out 2 of those. And when you use the tiles, that's called the zero principle, that the 2 of them add up to 0. So if I lift those 2 out, physically I can see, well, I'm left with 6x plus y in terms of the shape. Now I'm not saying, look, we need to ditch what we've done with the symbols. I don't think so. But some of the time we need to represent with pictures as well, because other learners use pictures. Joe?
How would you do that geometrically if it was minus 4y? Yeah.
Okay. Any ideas there? If that's minus 4y. Well, do you remember I held these up? That's what y looks like. Okay? That's what negative y looks like. So positive y and negative y, when you put those together, they add to 0. So it's as if they move out of your picture. So if you have negative 4y here, you'd have one of those left. It's got a different colour to this one. So that's usually where you start with algebra tiles. You can get students to build a particular expressions, but it's really important, this zero principle, that they'll add to 0 and disappear. So you'll be left with 1 negative y. I'm very conscious of what I'm saying here because there was a professor who came to the seminars before Christmas, and he was talking about visiting Irish maths classrooms. And he stressed the language sometimes he found unusual. How do you think that Irish maths teachers were pronouncing this? 3 minus minus 2. And he was saying, in the States we'd say that 3 minus negative 2. And he's probably correct in doing so. The difference between the sign as the operator and the actual sign on the number itself might also explain, when students say to you, what are these 2 minus buttons doing in my calculator? Well, there's your answer. So I feel like I'm trying to unlearn some bad habits, so I apologise if I say -2 when I mean -2. You'll forgive me? Okay, I hope so. Right, next. We were surprised ourselves with number 4. Tell me what happened in your discussions. So they started Mairead here and just worked from left to right. Yeah, and in our class we had 65% of students do that. Just work from left to right. Can I collect from you in the room, what are the acronyms that are out there? BEM, okay, BEMDAS? BirdMass. BOMDAS? BIMDAS? This could take days. Anyone ever heard of PEMDAS? That's from the States, where P stands for parentheses. There's also a GMA floating around there on the internet. We'll return to that in a few minutes. But I want to try a little experiment here, okay? Can you do a question for me, but can you hide it from the people at your table? So hide your solution, and then you're going to compare it to the people at your table. Okay? So write down your take or your answer to this question here. And all I need in this room is some discrepancy or some ambiguity between a group of maths teachers to illustrate my point. So Dave, I'm starting with you. What did you get?
0.9.
Point? 9. Okay, 0.9. Siobhan?
0.9.
0.9. Niamh? What did you get? 22.5. Pat? You got both of them, of course. Sitting right on the fence. Sean, what you get? 0.9. Conan? Now look, we've got 22.5 and we've got 0.9 in a group of maths teachers. The reason this exists is to handle situations like this one. So the correct answer is 22.5. Why? Okay, so the reason, like conventionally we have this in mathematics, an order of operations. Why is it that order, I suppose, is the place to start? Why do we have that order? Where does it come from? Some bearded guy decided one day. Like, can you see there as you move from left to right that the operations lose power? You know, you've got brackets, you've got exponentiation, mathematical dynamite, much stronger than multiplication or division, which is stronger again than addition and subtraction. So as we go from left to right, we've got the most powerful operators on the left, heading in this direction. But as Mairead said, they are inverse operations to each other. You know, sometimes you get the feeling with students that they're not aware of multiplication, what the multiplication operation really is. You know, a convenient way to add. So there's nothing wrong with working from left to right if the operators are of the same order. And they stress that, I'm not sure about here, but they definitely stress that in America. This is their PEMDAS. This is what the way they memorize it. Please excuse my dear Aunt Sally. But you tend to see it written as a pyramid, which is better, I think, than just in a linear fashion. So if we meet multiplication and division and they're the only operators, I can work from left to right. And same with addition and subtraction. Saw this on the internet recently. This stands for grouping, indices, multiplication and addition. But I was thinking about maybe for our purposes, could this be better? And to arrange it this way. So what do you think they stand for? Brackets, exponents, multiplication and Addition. So the fact I'm just putting multiplication there is almost implying that division is included, isn't it, with it? And same with addition, that subtraction is included or implied by it. Nothing wrong with working from left to right when I've got operators of the same order involved. How would your calculator cope, do you think, with that question from the test? Do you think your calculator will get the right answer all the time? Depends on? Yeah, it depends where you bought your calculator. Like if it's a petrol station calculator, it's a €7 petrol station calculator, this gives you 23 as the answer. Scientific calculators are correct. I saw this for €7 and I thought, like, isn't that how the maths teacher should be seen? Going off, oh, he's the maths teacher. Look, he means business with an absolutely rubbish calculator. So scientific ones will do it, but not those. The other thing I think that's important with our students sometimes is to try and convince them about this stuff. Rather than just presenting it as, here's how we do it, maybe use some questions to convince students that why we need an order of operations. So I'm going to take something this is from an Irish maths textbook. And it was tucked away at the end of the section on order of operations. Pencils come in packs of 10. I have 4 full packs and 7 extra pencils. How many pencils do I have? I want you to try and do that question for me, okay? No pressure now, it's not a tough question. But I want you to do it in a few different ways if you can, using a few different operators. Eileen, if I were to ask you, using the most basic operator, how could you answer this question? Well done. So there's a way to do it, a very simple way to do it. So what's the answer? That's 47. Are you confident about that? Yeah. Good. So we have the answer. We know the answer. Now give me a more complicated way if you like. Right, so 4 multiplied by 10 plus 7. I think we could use that in a couple of ways. Because there's multiplication, which is our convenient way to add those 4 10s, isn't it? The other thing we could do with this is, imagine if I reverse it. So if I say this is 7 plus 4 multiplied by 10. To students there, hopefully they see, you know what, it makes no sense to work from left to right. It makes no sense to add 7 and 4 and multiply it by 10. I'll get 110 pencils. Nowhere near what my actual answer is. Anybody have a third way? 5 by 10, take away 3. Could use that in a similar fashion, couldn't you? You know, you could ask the class, well, do I do that first and then do my multiplication? I'll end up with 35. So it doesn't make sense there to subtract before I multiply. Is that okay? Right, the question that we're coming to next, to me, is the big one. It's the biggest question to me of the 20. And it's number 5. Just sorry, before we get to it, there's a fantastic worksheet on the website. So if you go to projectmaths.ie and you go into workshop 5, there's a fantastic worksheet on order of operations. Really, really good. So it's got some context and it's got some pictures in it too. Question 5. Can I hear your comments first, please? This was the question that involved apples and bananas. So what do you think? Okay, Joe, so what do you think they'll give as an answer?
Either A or B.
Yeah, and I think, guys, you were saying in your group as well that they didn't link it to cost. Okay. Anything else? What's going on here with this if this question is difficult to answer? What's happening in their heads?
Looking at the A and B together, but not as representing something. I think we see A to be apple and B to be banana, and they're not seeing that it's the apple costs A because the A is the first letter.
Yes. And you know, the research says that too. The single biggest block to success in algebra is understanding what a variable is. And if we do go down the route of, if you like, fruit salad algebra, A is an apple and B is a banana, that may be okay for a particular class that you're in. It might enable me to add terms up quickly. But 2 weeks later, let's say when I'm multiplying, you know, if I've told a class you can't add apples and bananas, and then in 2 weeks' time, do you know what? You can multiply them. You can get a banapple, but we couldn't add them 2 weeks ago. That's a big issue. I had a student say to me about algebra, it's fantastic, you just use the last 3 letters of the alphabet all the time. You know, X, Y, and Z. And some of the textbooks are guilty of this too. This is another American textbook, where the textbook will stress it as a method. It's a narrow, really narrow definition of the variable. Later on, when the variable comes to represent quantities that are changing, A is an apple is almost a block. And I had a question up there just before we started. This was our warm-up problem. Because I wanted to tell you about what happened with this question with some real students. So I gave this to 3rd years, 5th years and Leaving Certs. They were all higher level. Can I take any attempts that you made first? Siobhan, you had a bit of work done on it.
Yeah, I did it 2 ways, maybe quick way.
Don't leave that a second. Give me the other way first.
So I had rabbit plus cat is equal to 10. So, and then r is equal to 10 minus c.
Okay. So did you just build that equation first?
Yeah.
And then you worked with it?
Yeah.
Okay. So you have r is equal to.
10 minus c.
Okay.
And then I had d plus r is equal to 20.
D plus r is 20.
And then I subbed in 10 minus c in base 4.
Okay, so you use the substitution method here. And you got d plus 10 minus c is 24.
Yeah, d plus c is equal to 24. And then that equation became d minus c is equal to 10. And then I did the simultaneous equation of that 2d is equal to
Okay.
24 and d is equal to 17.
So you worked down through it and got the dog's weight.
Yeah.
D is equal to 17. And then skipped up through the weights and found the total. That was A way. Right. Did anybody just build a system of equations to start with? Right, Phil, what did you write first?
R plus C is equal to 10.
Okay.
R plus D is equal to 20. C plus C is 24.
Okay. If we just stop there a second. In the Leaving Cert class, that's the way every student did it. Okay, built a system. Not as prominent in 5th year, hardly any students in 3rd year taught to build equations because they wouldn't be used to, you know, equations with 3 variables. And I noticed with the Leaving Certs, just going around looking at their work, if you take these two together, you'll end up with r, or c minus r is equal to 4. And in a couple of cases, I asked the students there, what's going on with that? Can you see where that is in the picture? And in a funny way, I felt like they were blindly using algebra here to solve it, without really thinking about algebra as the common sense of the situation. I mean, can any of you see that in the pictures? C minus r is equal to 4. Well, what's it saying to us?
If you take away a rabbit from a cat.
The difference between the cat's weight and the rabbit's weight is 4. Can you see that visually in the picture? So if you took the two of those together, we can see the weights are 20 and 24. The dog is common. How do I know that the cat is heavier? Because the cat with the dog is 24, whereas the rabbit with the dog is only 20. So there's a 4 unit or 4 kilo difference between those two animals' weights. Siobhan, you had a fast weight, and this happened in the 3rd year class. I want to see, is this the same as yours? I had a girl in the 3rd year class who said, that's a really easy question. And I was, how do you do it? The rabbit, these two pad, is it? Right, why? You have a cat and a dog common to both, but you've question mark. So that's the question. What do they all add up to? And that's what this girl said. If you threw all of those pictures together on the one scale, you'd have 2 dogs, 2 cats, 2 rabbits, and you get 54. Divide by 2, and you get 27. I don't know what it would get in the marking scheme. but I felt like she should have been carried shoulder high around the class, because that was really good mathematical reasoning to me. Siobhan, was that your quick way? Right. The key point I want to make here, though, anywhere I saw a student in 5th year or 6th year build equations like these, I asked them, what does R stand for? And what did I hear back? R is a rabbit. So what does 5R stand for? That's 5 rabbits, as opposed to R representing the weight of a rabbit. So we have issues around the variable. Here's the classic cartoon that you see involving the variable. You know, here we have, yesterday you told us x is 2, and today x is equal to 3. But there's a big point behind that. Think about what we tend to do with first year students. Would you agree our students would solve a lot of those equations in first year? And the solution to all those equations is one particular unknown. So sometimes students internalize that as, you know, x stands for a number. That's a very narrow piece of algebra, because what happens in second year when you get to this? 5x minus 2 is equal to y. Suddenly you're starting now to see the classic notion of what a variable is, representing a quantity that's changing. Whereas this is up here representing just one single unknown, isn't it? By the way, while it's up there, what's best practice for solving this? Add 2 to both sides. Why is that? Keeps the equation balanced. Why did I take plus 2? It's the inverse operation, yes, so it undoes, and it undoes that negative 2. What happens to these two? Oh, very good. So they don't. Not going to use the C word. So they add to 0. Very good. And you get 5x is 15. And then what do we do to both sides? Divide by 5. So you can really undo good work by saying cancel those. So 5 divided by 5 is equal to 1. So we get x is equal to 3. There's your single value that satisfies that equation up here. In a way, it's also linked to our order of operations, because we're getting rid of the most basic operators first, and then we're coming into the multiplication. I've learned in this run of seminars, 4 things make teachers emotional. Number 1, fractions. Number 2, how you solve quadratic equations. You know, I've used the big X all my life. Your calculator. I'm a sharp man. I will always be a sharp man. You won't convert me. Number 4, how to solve linear equations. And I had a teacher at a workshop in Galway, and she got really animated, just ignored me, turned to the group, said to the group, nothing moves anywhere. There is no movement in our subject. Nothing moves. So you know this idea of bringing it across and change the sign? She was saying that's horrific. Or even get all the letters on the left, all the numbers on the right. There is no movement ever. All we need to do is left hand side and right hand side, the same thing. And you know what? Usually it's undoing, isn't it? Mm-hmm. Usually it's the inverse operation. And I think she's right, because you can take 3 or 4 techniques that people typically use and boil them down into just one. Whatever I do on the left, I do the same thing on the right, and it's usually the inverse. The other thing, just while that's up there, what's the language that we use around this? So what word would you see before? Solve, yeah. In a couple of primary books I looked at, the question would be written like this: 5 times box take 2 is equal to 13. And the phrasing was interesting. It said, find the value that makes that sentence true. Which might be a bit better than solve, isn't it? It's find a particular value. You know, am I better as a maths teacher to solve 5x minus 2 equals 13 and then ask them to do it for 15 and then ask them to do it for minus 22, just to show them that this variable is taking on different values for those different equations. The picture, or the misconception that comes next, like 3x plus 3x is 6x squared. Have you seen that before? Yeah, and there's a couple of things going on here. The first is the fact that it's a multiple choice or test. There is a flaw of the student may just hop across and see the first one that they like. If the first answer appeals to them, they might go, well, that's fine, and not examine the other ones. But physically or visibly or geometrically, again, this is what you're talking about. 6x and 6x are 6 of those rectangles of area x added. Sorry, 3x and 3x will give us 6x altogether. I don't think any maths teacher in the world would be shocked at the misconception in number 7. You know, 2 bracket 2x minus 5 is 4x minus 5. And we could cut that off at the pass if we represent it visually. I was glad to see it at the table. Some people were saying, oh yeah, I draw the picture. I represent it with the block or the model. So this was work that we did back in workshop 5. Here's 2. This is 2x take 5. And what I found in class is I had to fill these in as well. I had to run around the shape because it wasn't always obvious that they were congruent lengths. Do you ever notice that in area and volume questions where you're working with irregular shapes and you're wondering why don't they see that they're the same thing? The advantage of the picture is that they're forced to distribute properly here, and I end up with 4x minus 10. And what I love about this is you can teach everything that we teach in algebra at Junior Cert with this picture. Like, what's the reverse? What's the reverse to what I've just done? Factorising. So if the question was factorise 4x minus 10, then I'm starting in here and I'm coming out. I still remember the question that I was doing with students in school when I realised that's the way I have to teach it. It was this one. Now, could you predict a really common mistake with this question?
0 n.
They're usually okay with the highest common factor of q, but I was seeing a lot of people doing this and almost ignoring that term. That doesn't happen with this array model because PQ plus QR take Q. They can see the common factor, okay, of Q into P plus R, but if that's Q, well, hang on, there has to be something here, and that's your -1, and there's your factors. Mairead, you were saying that you tried it for long division, was it? And effective?
Very.
Yeah.
I taught them both ways. I taught them the array model first and I taught them the other, and there's only 2 out of 27 of them doing the model.
Like the standard, yeah.
Yeah, the rest of them are doing, and they do very, very fast, and especially with signs and stuff like that, they're not making as many mistakes. It took them a little bit longer at the start, but they had a tendency to put in, like, if you are working backwards, that they might put the wrong thing in the second box.
Okay.
Like they'll get the first column right, and then the top, it took them a while to get that top box.
And
Once they got that.
so you're talking about dividing like an x cubed polynomial by a linear one?
In the square one,
Yeah, or a squared one, yeah. How many people have used that before? For long division? Okay, we'll do that in the afternoon. Do you remember that Christian brother I told you about? He described long division as daddy, mammy, sister, brother. The daddy, mammy, sister, brother method. Did you ever hear that before? Divide, multiply, subtract, bring down, start again. Divide, multiply, subtract, bring down. So we'll look in the afternoon because Mairead has volunteered to come up and explain the long division method. Look at this student. You won't be shocked at this. This student gets it right. It's 4x, take 10, and look what they do next. So the equal shows up on invited again, and of course equal to 0. You'd wonder why did they stop at 2x as well, at 2x equals 5. And you know, I feel with lots of these discussions that we're having, they're irrespective of syllabus. You know, this is really nothing to do with project maths, or these are issues that are there in the teaching of algebra, full stop. I'll show you what I mean. This question 8. Have you ever had a class where you think everything's going really well, and then you get to transposition of formulas, and the wheels sort of come off a bit? And the researchers say here is, the problem students have, if they've learnt moving across an equals and changing a sign, these questions are especially difficult. Or if they've learned get all the letters on the left and the numbers on the right, Well, what do you do if you don't have numbers? Well, I'll give you an example. Here's a question from the old course. This was asked in 2010, Higher Junior Cert. It was question 5, part A, and you had over 50,000 students take that paper. Could you guess the percentage of students who got it correct?
I think the square ones are probably fairly low.
Okay. About 9%. And the most common wrong answer, according to the correctors, was this. So, you know, I'll just swap those two. Students tend to invent techniques sometimes on the day of exams. Probably not the best day to become famous for inventing something in mathematics. You know, I remember I used to say to Leaving Certs, if you're doing something that you've never done before on the day of the exam, something's up. Take a look again at what you've just done. Like how could I get out of that? Phil, you mentioned it there. If I want to free up x, square both sides. And it's the same thing again, isn't it? It's this undoing process, like we saw with the basic linear equation. And the reason I think it's so important is it's consistent right the way up through the Leaving Cert. That's all we have to teach, this undoing. You know, if you have a derivative and you want to get the function, how do you undo that? With the antiderivative, isn't it? Or if you have, let's say you're solving an equation, trigonometry, sine x is equal to 1/2. How do I undo the sine x? Or to undo the sine function, introduce the inverse sine function. So we get x is the inverse sine of 1/2. And that's exactly what we've been saying to them from first year with basic linear equations. Calculator even has that on the screen, doesn't it? Yeah. Inverse sine 1/2. Okay, the next one, and we'll do a couple more before we go for coffee, okay? Look at our stats on it first. So we've 90% of students who made a mistake with this. This is the question I was mentioning to you earlier that's on the Leaving Cert for 30 years. Same mistake over and over again. It doesn't respect boundaries either. You could see a second year do it. You could see higher Leaving Cert do it. You could see people in third level do it. So maybe it's an indicator that we need to do something different in the teaching of it. Can I get you all to try something for me? It's x plus 3 to be squared. Could I get you to attempt a picture of it? Draw what you think it looks like geometrically. Okay, so usually we will get the x squared plus 9 in any answer, but it makes them, I suppose, pay attention to these here, isn't it? Do people get them to gather terms along diagonals when they're getting their answer? That this is plus 6x, and then you've got x squared. People do that? Because that is important in your long division method, that you can see it at that angle. And that this is the only place you can have x squared, and here's the only place you can have a fixed constant, plus 3 multiplied by plus 3. I think if you're going to use it in your school, though, you'd nearly need the whole maths team using it. Because if it's just you using it, that's a bit of a battle you have to fight. The other point to make about it, students probably need to see that in number first. You know, in a sense, if I just drop it in algebra, it could be too late for some of them. So all the basic number stuff I can do with this model as well. I want to show you something here that a teacher gave me earlier this year. We were discussing this, and I call the next slide the Sarah Jessica Parker slide. You know that actress? Because apparently Sarah Jessica Parker divides people 50-50 in how she's perceived. So apparently females see her as she's an attractive actress, and men tend not to agree. This slide is the same. If you like it, use it. If you don't, forget about it. Because I do realise this could get people emotional in school. This is called the dead puppy theorem. So every time you do that, a puppy dies. Now I know it depends where you teach, but here's the point. This teacher said to me, since she started using that in the classroom, she's noticed students almost self-correcting or almost on the lookout always for this error. She heard one student say to another student, "You killed another puppy." You know, so they're on the lookout for it. They won't forget it. If you like it, all you have to do is Google dead puppy theorem. There is a corollary too called the dead kitten theorem. That's what I was thinking. It's probably a bad week with Crufts to be talking about this stuff. But like I said, take the bits that you like. Now a couple more and then we'll go for coffee. This is number 10. Tell me what you said here.
Magic cancelling.
The magic cancelling, yeah, crazy kung fu. The girl that gave that answer, part C, she said you can divide 5 into 20 because 20 is a number. You can't divide 5 into 5a. It's not a number. A plus 20 would be common too, wouldn't it? You know, cross out those 5s. What about the last one? A is equal to minus 4.
So the last one is kids like to get an answer.
Do you like to get an answer? Has to be something. Yeah, and so equal 0 shows up. One of the schools, in the maths conference last year in Maynooth, one of the schools took a look at cancelling and they came to the conclusion that nobody in the school should use it. And in their discussion around it, they come up with something I thought was very interesting. They were asking teachers who attended their presentation, how do you simplify 8 over 12? And most teachers said, well, I divide 4 into the top and 4 into the bottom, and you get 2 over 3. And the girl was saying, yeah, we agree with that, but now we're starting to think that's probably not the best way to do it. Probably when we're working with numeric fractions at the outset, we should factorise. So 4, highest common factor is 4, so that's 4 times 2 over 4 times 3, and then 4 divided by 4 is 1, and I end up with 2/3. Now I know it's probably a little bit longer than what we do, but her point was, wherever we meet fractions, that's the process. So instead of having all these techniques that they have to remember, it's like the equations one, just undo on both sides. Whenever I meet a fraction and I want to simplify it, I factorise. Take the one that's in the competency test. 5a plus 20 over 5. And I want to simplify it. It's a fraction. So factorise and I get 5 into a plus 4 over 5 times 1. And 5 divided by 5 is 1. And I end up with a plus 4. So I can link it back to what I do in number. And there's so many examples of that. Have you ever noticed you can be doing work in algebraic fractions and the students think, you know, this is almost nothing to do with the fractions we did in number. But again, it's a fraction. How do we simplify fractions? We use factorising. Another place where you might find it useful, you know, when you're using your quadratic formula, it's a fraction. So instead of introducing another rule like split this in 2 or multiply it by a quarter, it's exactly the same process. Highest common factor is 2. So if 2 into 4 plus minus root 2 over 2 into 2, and 2 divided by 2 gives me 1. So can you see this idea of having consistency through what we do with less tricks, with less, like you said, Phil, less magic cancelling, you know. Right, 2 more then, and that's your dead kitten corollary. Every time you do some crazy kung fu or mathematical cancelling, a kitten dies. Okay, 2 left. 15. Now tell me what you think yourself first. These are 2 questions on indices. So what do you think's happening in 15? What would you predict? Go to the tables, yeah. And yeah, you'd hope to be able to apply that properly, wouldn't you? The problem with the tables is it's in terms of A, which could be another issue. Look at the answers we got. 75% of the students answered it incorrectly. First answer, x to the 52. Yeah, so the bracket doesn't mean anything. Or x to the 25, Kira, you had that, didn't you?
Yeah.
So just square the 5. Look at this third one. I think this is a really important one. x to the 7. Yeah, because in multiplication we add the powers. So that could be an informal shortcut here that the teacher uses, which is fine for that lesson, but might come back later and get you into trouble. One teacher that I met said the best way to teach indices is get the students to convince you that the rules work. So don't see them as a set of rules that are outside of this that you bring in, And she said, it means writing them out longhand until you feel like they have a handle on it, so that they can see what's happening. Because you know yourself, if they don't fix this in algebra or number, then calculus is going to be very difficult. Like, how do you do integration if you can't handle indices? Last one I want to look at is 16. And before I ask you a question around it, I just want you to see what students wrote. Which of the following is equal to 5 to the 0? It's equal to 5, the student said, because the small 0 stands for nothing. So it has to be 5. So it's 0, it doesn't mean anything. Or, yeah, I like that one too. 5 to the power 0 is 5, as there's no sign of an indice. No sign of an indice. And this is nice too. It's simply 5.